Am I audible? Okay. So good morning all. I am Kaushal Buch. I work with the Giant Meteorology Radio Telescope located near Pune. And as is mentioned, talking about radio telescopes, some part of the instrumentation used in radio telescopes, how radio telescopes, which are very sensitive radio receivers, how they deal with power line noise. And finally, power line noise is also a concern for ham radio. So how we can draw parallels from radio telescope instrumentation and use them in ham radio applications. Okay. So, giving a brief about what radio astronomy is. First, we begin with the, in general, the astronomy. So, we all know that when we usually think of astronomy, we think about the optical one, where we can look at different stars, planets through a telescope, right? An optical telescope. Uh, and so that is one spectrum in the whole range of electromagnetic frequencies. That's one spectrum in which we often do radio astronomy, I mean astronomy. But we have, as you can see in the first, okay. So as you can see, there are different, in the first plot, you can see that there are different frequencies. And it starts all the way from radio spectrum and actually goes all the way up to X-rays and gamma rays. So today the astronomy that we is done at several frequencies, starting from radio all the way till gamma rays. And radio telescopes in particular use that radio spectrum, starting mostly with the HF and going all the way up to terahertz kind of frequency domain. And the bottom plot basically shows that the atmosphere is opaque to certain frequencies and it allows certain frequencies to pass. So the radio waves can reach the surface of the earth and therefore it is possible for us to do astronomy sitting on the surface of the earth. Whereas if you go to higher frequencies like UV, X-rays, they are blocked by various layers in the atmosphere, and hence you can't. You have to do satellite-based astronomy for those frequencies. And each of these frequencies give some idea of the uh, phenomena going on in the celestial objects like stars, nebulae, supernovae, whatever. So those things can be captured at different wavelengths, and you understand the physics going on in those sources. So, for example, a particular source like a galaxy, you can see here that in radio wave it appears a little different. It gives different information about the source, and when you go all the way up to X-rays, it gives a different reveals a different kind of information about the source. So today, as I said, we can do astronomy all the way from radio to X-rays. Of course, the today's talk will focus on the radio window, and it also has a lot of things to reveal. So the history of radio astronomy is something that started almost serendipitously. So Carl Jansky of Bell Labs, he accidentally discovered some radio emission coming from extraterrestrial source in 1932 while he was looking for static noise in communication devices. And then finally it was concluded that this noise came from the center of our galaxy, that is Milky Way. And that was reported in the paper titled Electrical Disturbances Apparently of Extraterrestrial Origin. And then that started some interest in looking into the universe at these frequencies. And then Gorote Reber was the first one, the bottom part of the slide, who built a parabolic reflector. And this was the first dish antenna to be used for radio astronomy. It was a 9-meter dish, the one which is shown here. And with this, he was able to carry out an all-sky radio survey in all the directions to see what the emission looks from when it comes from extraterrestrial sources. And he built maps of the whole sky at around 408 megahertz. So this is the kind of history with which it started, and that started a new window of astronomy. So if we look at just one example of the Jupiter that we know from our optical images and from the way we look at it through a telescope, is in the lower part of the slide, which is in the visible spectrum, right? But if you see the same thing, if it is observed in the 21 centimeter, which is about 1420 megahertz, in radio you can see some extended emission coming out from this, which is due to the magnetic field around Jupiter. So this information was otherwise not revealed through an optical medium, but which gets revealed through the radio medium. So similarly, different wavelengths can tell you different things happening, and so it's important. Similarly, if you look at galaxy, this is a Centaurus A galaxy, and the left one is the radio image. You can see that the extended emission from the center of the source, the lobes coming out, they are very clearly visible in radio because they have certain phenomena which apparently is more prominent in the radio wavelength. And the other part of it, which is seen in the optical image, is not visible in the radio image. So they complement each other in some way, give idea about things happening in different wavelengths. So what does a radio telescope do? In a very basic sense, uh, it is basically it's a radio receiver. It's a passive receiver. It observes the emission coming from celestial objects at different frequencies, and it studies various stellar objects, as I was telling about, stars, galaxies, and pulsars and quasars, and you name them, and most of them are observed through radio frequencies. And so you point a directional antenna towards a certain part of the sky where you have a source of interest, right? You want to observe a certain source. You kind of measure, so you measure the direction, you measure the power of that source. Power is a function of frequency of that source in certain direction of the sky. And as the earth rotates, you keep tracking the source and you keep getting information of the source. Now this is a very basic single dish receiver kind of thing, and mostly we want to observe the thing in wideband, because I'll come to why we want a broadband receiver. And as you can see that a very basic way is to observe with a directional antenna, have basic amplification, down convert RF to IF, and then do a detection of power coming at a set of frequencies in that direction. So if you, the signals coming from the sky are mostly random. It's like random noise, Gaussian distributed noise. So if you see the top plot, it shows this is time on x-axis, or maybe sample number. It's a digitized time series of signal coming in. It's completely random, as you can see, the amplitude being on the y-axis. So in such cases, for noise, we know that noise, the power is in the bandwidth. So the larger the bandwidth, the more is the received power. And hence we need to observe this the sky at at a wider frequency range. Okay, and the signal received is very low. So if you measure the power spectral density, right? So it is about the unit of measurement is called 1 Jansky, in the honor of Carl Jansky, who actually first discovered emission coming from extraterrestrial source, is 10 to the power minus 26 watts per meter square per hertz, right? So you have normalized it with the collecting area of the antenna, and you have normalized it with the frequency of the, the bandwidth of the receiver. So that is about minus 204 dBm, right? So if you see if you want to compare it, the GSM handset sensitivity is minus 111 dBm for the given specifications at 1.8 gigahertz and 200 kilohertz bandwidth, and for isotopic antenna. So this is 93 dB below the sensitivity of what the radio telescope receiver needs to detect any source, radio source. So we are operating in a very extremely low signal to noise ratio. And if you see the typical power coming from various sources, like the quiet sun would have about 10 to the power 3 Jansky. So even the strongest source is about 10 to the power 6 Janskys, which will still be much lower than any commercially available sensitivity of any commercially available receiver. So okay, I don't think this is. I was just trying to show you the sound of noise, but that's fine. Okay, so now I come to GMRT, and because this has an operating frequency range which overlaps with that of ham radio and so on. So if GMRT is again with single dish you cannot achieve the kind of sensitivity that I was talking about. So you need an array of antennas, and you need a wider collecting area so that you can have better signal to noise ratio. So we have 30 dishes, each of 45 meter diameter, spread in an area of 25 kilometers. And as you can see here, there is a cluster at the center of this map where there are about 12 to 14 antennas, and the rest of the antennas are spread in three directions in a Y-shaped pattern. And it is one of the most sensitive radio telescopes operating in the range of 130 megahertz to 1450 megahertz, and has a maximum bandwidth of 400 megahertz, and it's fully steerable, so you can so you can track any source from rise to set in any direction. So what can GMRT, in common terms, it can detect cell phone signal if you are radiating it from the moon very clearly. It can detect FM radio emission from Saturn. These are just parallels to what we talked about, the sensitivity numbers, just to relate it to more common emissions. So airport radar, if it is kept 4.2 light years, GMRT can detect this, so it's that sensitive. And the angular resolution. So the reason why we are separated about 25 kilometers is to get a good angular resolution, because the sources in the universe are far away and they are huge. They are huge, but they are far away. So the angle that they subtend towards us is very fine. So we need a very fine angular resolution. So this we get is about 2 arc seconds, and 1 arc second is 3600th of a degree. And just to give you some perspective, the sun as seen from Earth is about half a degree. Okay, so we are at 1/360th of a degree, so we can resolve that kind of finer object. I'll show you some footage of few antennas. These are the nearby antennas from that cluster, and you can see these are the 45 meter diameter dishes spread across the 1 square kilometer area. And you can see that they have a mesh as a reflecting surface, because at these frequencies the mesh appears as a solid surface, so we don't need a solid reflector there. So these are reflector based dishes, and that is what has made it possible to build such larger dishes and operate them in terms of the weight and steerability. Near Pune, it's 80 kilometers north of Pune. No, it is close to RV, about 25 to 30 kilometers from RV. Okay, so if you see a very top level picture of how the signal processing happens in a radio telescope, so you have an array of dishes, and generally they are very directional like these antennas, and once the signal is received, there is a feed at the focus of the parabolic reflector, and that's where first level of low noise amplification happens. And then these RF signals are either they are converted directly at the base of the antenna and sent it over some medium like an optical fiber to a common location, because we need to process the signals at a single location. So we need to bring the signals from different antennas to a common location. So that's what is done here, and then you have a central station where you digitize the signal, you do what we call the correlation. So basically all these antennas are looking at a single source, and you want to see the similarity of the signal coming from each of these antennas, which will give you information about the radio source being observed. So this is the basic picture. Now if I show you the RF systems at the top of the dish, so this is that reflector, as I was telling, this is a dish, and then you have here because we observe a large range of frequencies, it cannot be covered with one antenna. So this is what is called the turret, on which there are 4 feeds mounted. So the one is pointing down, the one towards us, one towards the sky, and the one at the focus of the dish, pointing towards the dish. So when you see this, you would see that there is a horn antenna right here at the dish, which is focused towards the dish. So that is the one in this picture which is currently picking up the reflected signal from the parabolic reflector and processing it. So what are the challenges for us? Because as I said, we are extremely sensitive and passive receiver. So when that happens, the first thing is that you are vulnerable to interference, because you are observing a wide range of frequencies which are or are not licensed to you. And because you want more sensitivity, you need a larger bandwidth, you need more collecting area, you are more sensitive. So we have a range of different kinds of interference. So if you see from air traffic control, satellite, mobile, these are all what we call the narrowband interferences, which are confined in a certain frequency range. And then in the bottom left, we have the RFI coming from power lines, automobile sparking, which is a source of broadband noise. So it causes a broadband uh, corruption of the spectrum, right? Yeah, there was a question. Yeah, so any sparking event is a cause of electromagnetic interference, right? That is how first J.C. Bose has demonstrated through a spark gap the generation of electromagnetic waves, right? So sparking produces broadband interference. I mean, it is interference for us. It produces a range of frequencies uh, when there is a sparking. Okay. And for us, because it interferes with our reception of signals, so we call it interference, right? So sparking on in spark plugs, in power lines, that is a source, and that's how also it comes to ham radio also. Ham radio also, if you are located very close to a transmission line or a transformer, it gets coupled with, and sparking is the primary cause. Corona discharge and sparking, these are the primary causes of interference. Corona is more at HF, and sparking is more into UHF, VHF range. So now coming to, because I'm going to focus more on the power line noise, so we will talk about the sources there. So this is something you can see. These are different ways in which the power line noise, we call it RFI because our signal itself is noise. So we call it interference and noise. So that term I will use as interference, but it is also called power line noise in ham radio. So uh, so this is how during sparking or corona you can see that huge burst of impulses, high power impulses is generated, and that gets intercepted with by the antenna, and because it's the same frequency, it interferes with the uh, receiver. So in one of the things which we find in many cases is that this is the high power transmission line somewhere around the GMRT array, and you can see some kind of conductor is the strand, wire strand is located. I mean is there, and this causes sparking and this causes interference. So, so if you see, there are many potential sources like these fuses and dropouts. These all start these dangling wires. They can cause sparking and they can cause interference. So if you go into more detail, if you want to build some system to mitigate this, because it's a uh, very much of a problem when you have a sensitive receiver like ours, then you need to understand the kind of properties of this. So again, if you take time is on x-axis and the received voltage is on y-axis, these kind of sparking occurs as the impulses that you can see. So this one where there is no impulse, where quiet is the noise, which is of our interest. But you can see that there are a bunch of impulses coming out, and this bunch are repeating at every half of the frequency of the power line. So 50 hertz. So 20 milliseconds is the period of the sine wave. So every 10 milliseconds you can see the sparking repeating, and it comes in bunches from different sources, and it could be many things. There could be multipath, there could be various sources, and so this is how you can map it with the AC cycle in some way. And this keeps on changing, the signature keeps changing depending on how it is intercepted by the antenna and from where it comes and so on. So this is one such frequency at 325 megahertz from one of the GMRT antennas. Now, why this was very important for us was that there are a huge number of power line sources which could be potential sources of power line interference. So this is again the map showing the GMRT array in blue dots, and the number of transformers and the location of them around the central square, and that is in red. So you can see a huge number, maybe about 100 or so. And then all along the south arm again I have shown. There are all along all the arms. I am just showing an example of central square and south arm antennas. So the first level of finding faults is to go and look at it through an ultrasound detector and look at various sources like the pin insulators and so on, and then sorry. No, no, these are ultrasound detectors. So you point, so this is a dish, I'll show you in the next. So this person is holding a dish and is looking at different places, different joints, links in this particular substation kind of setup, and he's trying to figure out from where he gets the maximum radiation. So first level of any mitigation is at source. So you try to get rid of the interference, but since there are too many interfering sources, you need various places where you can mitigate. So again, this is one log periodic antenna in the on the top left, which is measuring some interference coming from a base station, substation, and this is the kind of thing which I was talking about in the next image, which you can point and you can see, and then you. Because in an observatory, you should not be your own source of interference. So you should not radiate. So these are, the next slide is all power line filters. So we want to protect our own antennas from our own RFI. So these are some of the devices which we have to use so that we don't radiate and we don't disturb the signal. So this is one level of protection. You go and try to stop at the source, but there are too many, not always possible. Then you do things to protect yourself and your own antenna system from your own RFI, and something at circuit level like building a toroidal coil and so on. And then the third place is to have it in signal processing systems. So today I'll be talking about this third one where we do mitigation. Yeah. Yes. Yeah. Yeah, we replace it with. Yeah, sometimes it is not proper, or these kind of fuse links which I showed, right? These kind of fuse links which are not. No, you can replace it. No? You have to replace it. And okay. So if you want to build something in the signal processing level, you have to understand the signal even better, like the thing I showed a couple of slides back. So again, this is a more high resolution, the top one, high time resolution plot taken from an oscilloscope from one of the antennas at 550 megahertz of GMRT. So you can see these bunches are very clearly repeating, and all that impulses that you see is all due to power line RFI. And the places where there are no impulses are the places which are of our, which are important to us. I mean, even those where impulses are there, it is important, but they have been corrupted by power line RFI. So the earlier we do damage control, the more we can retrieve the data. So, and if you see the same plot in spectrum analyzer, so if you do a zero span mode where you have only, you can plot time scale on x-axis, then you can see that these are the bunches again repeating every 10 milliseconds. So if I have to show you a video of this, you can zoom in, and it's a composite signal. It's not just those bunches, okay? Within the bunch there is good signal. So if you, now I am zooming into, so there was a collection of, there are a collection of bunches. Now there is one bunch where you are zooming into the bunch, and I think it's a bit slower because of the. So now you can see that within the bunch there are many sparking events which are happening, giving rise to this impulse. And if you now if you zoom further, you will see that there is good data between the impulses that are occurring. So you can see as we would zoom in more. Yeah. Yeah, so now you have come to a level where individual impulses from power line RFI are seen, and you can, so this noise which is seen is of our interest, which is still good, which is not corrupted. So we don't want to just remove that whole bunch. We want to find a solution which can selectively remove only these impulses. Okay. So first we built a filter where everything here has to be done in time domain, because once you go to the frequency domain it becomes broadband, so you can't put any notch filter or any band pass filter or anything. So you have to do everything in time domain. So you first get an estimate. So the bottom left plot, you see that first we have found out in this noise what is the typical power of the incoming noise, which we do it in real time. We get the value of that, and we establish a threshold that anything that comes above this threshold we will term it as interference and we will remove it. So by removing, we either replace it with a noise, or we can replace it with zero. We can blank it. So there are many blanking circuits even in ham radio you will find. So similar thing we can do here. So this is one early example of how you can see. So the blue one is the unfiltered signal, and overlay plot is red, which is the filtered signal. So you can see it has picked up all these strong impulses of interference, and either it has blanked it with a zero value, or it has replaced it with some known value of noise. And this was tested on hardware like this. The top setup shows that, but this was only single. It was only module level testing. Now when we go to the entire signal processing backend of GMRT, which is the one shown here, which is a complex system with multiple nodes of high performance computing machines, and the front ends contributed through programmable chips. And then you see this image, which I'll come to in the next slide. So you get an image which is then filtered. The power line gets filtered, and then we build this image. But this solution can be extended to multi-core CPUs and GPUs, which are now being used quite widely. So again, just to give you that the system which we built, so if you see frequency and time, right? So you can see on the x-axis we have started from 550 megahertz to 650 megahertz, 100 megahertz band. This is a time frequency plot. You can see that the intensity is shown by color, variation in the color. So yellow one is the one which is having higher intensity coming from power line RFI, and it is repeating every 10 milliseconds. These horizontal steps, they are repeating every 10 millisecond, and you can see in the filtered version they are completely gone. So it has picked up and removed. So this again, these steps are coming from that sparking in positive half, sparking in negative half, and the repetition of that. So this is one test. Now if you go for more astronomical tests, so this is some source, some radio source, extragalactic source being observed by GMRT at 550 megahertz. You can see that we did a simultaneous testing of what happens if we filter the data and if we keep the thing unfiltered. So simultaneous testing. So you can see that this is the unfiltered data, where you can see around the center of the source there are a lot of artifacts, and which are completely removed. So this is much cleaner image achieved through filtering. And similarly, if you see some pulsating sources like pulsar, where you detect the pulse, so the detection depends on how much is the difference between the peak and the noise floor. So that is much improved after filtering, and you can easily detect the pulse. So now how is it relevant to ham radio? So we have huge frequencies which are, there is an overlap at VHF, UHF, and there is also a problem of power line noise in ham radio. So I don't know this, okay, this is, yeah, is there audio? Okay, anyway, I had taken it from internet and I wanted to show you how the power line noise sounds like in ham radio. Okay, it's fine, I think. You want to? It's not coming. Maybe some it's not able to catch. Anyway, so basically it was just a kind of hissing noise throughout the thing, and anyway, I've taken it from this link, so maybe you can also have a look at it. So basically, there have been some efforts and in mitigating power line noise in the ham radio receivers. So this is one amplitude modulated signal, and the spikes here, the impulses, which I showed in a different context in for the GMRT thing, uh, they are picked up by this noise blanker. So basically, you have a comparator, and again you have a threshold. So you establish the threshold, and you can selectively remove these impulses coming, and you can get the attenuated power line attenuated signal, so that you can get a better reception. But what I am trying to also extrapolate from here is that uh, this can be done at multiple levels. So if you have an SDR based radio now, you can build this solution in the typically in the FPGA if that is possible, but that may not be possible when the if you are not building one. So the thing could be done, the whole thing can be done in the SDR software or in the kind of reception that you get. You can use the same algorithm, you get the detect the power level, establish a threshold, remove blank everything that comes above the certain threshold, and you can keep that threshold variable so that you can play with it, and so you can tune it, and you can, so this the whole concept which has been very successfully used at GMRT and has been used for mitigating power line interference can be used in the ham radio receiver. So basically you can determine the power level, set the threshold as I was telling, and blank the noise part, noise power line noise part. So it has the solution can be in the analog domain. So if you have an op-amp based thing or something, you put a comparator, and if it is digital, you can directly use the same logic but in the digital system, and you can also use similar thing in software. Yeah, there was a the one which the one which we have built. So it has been it is there, but it is in a very different context. So it is there in open source, but there is a different FPGA library. But we can think of doing the same for software part. Maybe we can discuss it offline if you. Huh? Yeah, no, I'm done. So these are the links and some of the papers for the work that we have done at GMRT, and these are some of the things in general for the ham radio. And there is an article on this topic in the HamFest magazine. You can the last page, I think, last 2 3 pages, and you can refer to it. And yeah, so I would like to acknowledge the HamFest organizing committee for giving me a chance to come and talk to you. Thank you.
In our shacks, we are trying to reduce the RFI coming from LEDs and this and that and all of that, right? When you showed that you're reducing power line noise, at least I was very happy in that context. But two questions. One, when you are making sense of those signals, when you cut it off, let's say this is noise, this is like, let's say we look at a pattern and then remove that noise out of the signal for you to make sense. But don't you think the noise coming from far ahead can also have patterns which you might effectively cut off in your processing?
Yeah, so I think I'll repeat the question. I don't know whether everybody heard about it. So you said that when we are removing a certain part of the signal, thinking that that is the power line noise, aren't we removing anything that is useful? Okay, so one thing is that this gets superimposed on that. So that part is anyway gone. So that part of the observation is anyway gone to RFI. We are only doing some damage control by removing it. And there are very few sources in the universe, known sources in the universe which will have a trend which will be very sharply rising like this impulse. Yeah. Hmm. Okay. Maybe we'll have to just. No, we'll have to think. I'm not really sure. Yeah. Maybe we understand exactly what you are asking. Yeah. Yeah, I got your point. Yeah, I got your point. We just need to, yeah, a little bit think about it and see.
To give a memento to Mr. Kaushal as a token of our appreciation. Now we will be having a session by Dr. Shahjahan Kutti on the topic of beamforming.